Thank all of you for coming out and joining us for this Halloween edition of ZOS or AI for ZOS SysProgs. And I guess I might begin by just saying, why would a SysProg even need an AI? Well, I guess in the global scheme of things, we have to step back a bit and realize how complicated a system programmer's job is. There's a lot of detail, there's a lot to be responsible for, and there's a lot to be held accountable for. And so any assistance of any kind that is practical and provides true help is something that should really be considered by an organization. So let me try to explain a bit about how we see AI and level set us all to a sort of a standard, if you would. An AI model is essentially a smart program. What it goes on in its development is that a data scientist essentially trains it either using supervised or unsupervised techniques to perform a task, the output of which is hopefully could be viewed as something smart. What the problem is that we're trying to resolve is generally viewed as having to be complex, and system programming fits right in there. It wouldn't make any sense to build an AI that is solving a simple problem. There are lots of other ways logically that could be done. So the data scientist takes on the responsibility of picking apart some complex issue, for example, the IPL path of a ZOS environment. That's something we'll talk about, and begins to apply his or her techniques to actually encoding rules and paths through that model that will give it the ability, once prompted, to produce a finding that we hope will be something smart. So the answer should often lead to action. That is, that the answer isn't just an answer for the answer's sake. The answer is an answer that will lead you to taking some action of some kind. Perhaps fixing a problem, perhaps upgrading a PalmLab member to a new release of the operating system. So on the other end of the spectrum, data science on one end and decision science on the other, the decision science position here is where you play a role, because you're the one who really in the ultimate has the ultimate responsibility to determine if the model is actually doing something smart. And because of that, we offer additional client briefings on the underlying details of how all this works, as well as proof of concept trials that allow you to bring in these models and try them in your own environment. Our technical support staff would be with you every step of the way. So realize that even though people may talk about AI and its ability to do something smart, that part of the whole process, that flow that is doing something smart, really depends on decision science. That is you looking at the results and saying, yes, I see that, I understand it, I know how it got there, and that looks like something smart has taken place. Now, there are different kinds of AI models. You see four general types across the top of this rule-based models, large language models, LLMs, generative AI models, and RAGs, RAG. These are uh, retriever augmented generation models. These are the latest and greatest forms of AI that not only use generative AI, but depend on the rule-based models that we're going to talk about in just a moment. The rule-based models are basically if-then statements. That is, it's just a whole bunch of them. If this condition occurs, do this. If this condition occurs, do that. If this condition occurs again, report a finding to someone in the form of perhaps an alert. Both the rule-based models and the large language models essentially predict. In the case of the rule-based models, they might predict a finding that's based on, let's say, an understanding of ZOS ParmLab syntax. In the case of a large language model, they might be predicting the next word or the next tone or the next pixel. Their whole purpose is to make a prediction, a single prediction that can extend the understanding, their understanding and your understanding of the environment that they are performing their task in. This is different from generative AI models and RAGs, which actually generate something new. They generate generally something unexpected. They generate complex pictures. They generate complex molecules. They generate complex, excuse me, astronomical phenomena and events, things that people have never seen before and have to, in fact, perform that, uh, excuse me, perform their task on it of making a decision as to whether or not that information actually makes sense or not. As far as training is concerned, the differentiation here is that the rule-based and large language models are supervised in their training. The rule-based models are fact-based retrievers. That is, they are based on documentation and understanding and experience of the data scientist. And quite often, as you'll see here in just a moment, they don't take in information from the environment as part of their training, but in fact depend on their ability to retrieve information from the environment as part of their process itself so that they can produce a result that is based on the real world state of the environment at the time at which they perform their task. And I'll explain that in just a moment. Supervised LLMs actually take in large amounts of labeled data sets. And those labeled data sets are cleaned and groomed and processed through what are often referred to as tensor models that repeatedly process to the point where they produce an array of potential outcomes. And the one that is selected is the one that the model believes has the highest probability of being the correct answer. That method doesn't produce a 100% result. It produces, let's say, 98%. And so at some point, the model will get it wrong, and we often hear that as a hallucination. The same thing is true with generative models. They are unsupervised. They are trained against very large data sets of unlabeled information, so they learn on their own. And their ability to predict is even lower. Most people think that it's at least a couple of percentage points, maybe more, below the predictive capability of an LLM. And on the other hand, the RAG ones, that is, those that are retrieval augmented generators, that is, they incorporate both rule-based information and rule-based training as well as generative training, have a higher probability of getting the right answer, but still not 100%. So it should be clear from this that there are a number of different potential model choices that can be talked about that could be applicable in a ZOS environment. But if you're a systems programmer, you don't need something that's guessing and potentially hallucinating to give you the assistance that you're looking for in order to care and feed your ZOS environment. The best choice here is a rule-based environment, and that's what we have chosen. So let me explain a little further. This is a basic diagram of the models that are included in IPLCheck AI, which is a derivative work of image focus, and how it functions. The data scientist, as you see here, has essentially 5 different sources of information to deal with. His own experience, your experience, general experiences from Share as an example, or other uh, groups of system programmers that gather around the world, from PTFs that are made available on a regular basis, from formal documentation, and then some other inputs that he also has to take into consideration. It's possible that you could supply information that will impact the training of the model itself. For example, a test parm data set that you would like to have included in the concatenation so that you could test other changes that you need to make that might be taking you to a new release of the operating system. The second thing that he has to consider that you might provide are weights and biases that change the outcome of the model itself. The outcomes, we refer to them as findings, are presented as either errors, warnings, notices, or informational. But you may object to that. And so these weights and biases allow you to say, no, I don't see that as being an error in my environment. I would rather change that and turn it into a warning. This is all possible, easily possible, within the construct of the model itself, both the formal training, which this data scientist does, and then the on-prem training, which you do by providing either a test parm log, if you choose to do that, or additional weights and biases, which will impact the performance and the output from the model itself. Once the model is stabilized, that is, it has all of the inputs that it needs, it's essentially prompted automatically in the case of running under the IBM Health Checker for ZOS with information about the unit address and load parm that would be necessary to kick off an IPL. And so with that prompt, what we're going to do is we're going to build a virtual environment that is a ZOS system, whether it's 2.5 or 3.1 or 3.2, makes no difference. It will function as if it is a fully functional ZOS environment. It will begin to extract information from the running system itself. Tell me what your parm lib is, tell me where all the members are, tell me what your APF list is, tell me where all the modules are. All of these things will be repetitive prompts, somewhere on the order of between 2,500 to 3,000 in a normal inspection. Each one of those may result in additional prompts. Remember, these are if-then statements. So as it's finding stuff, it's continuing down its path, trying to complete the inspection in the best possible, most efficient way to result in a finding, again, of an error, warning, or notice. Of course, this is a somewhat laborious process, and the trace from this process can be extensive, on the order of between 15 to 20,000 records long. So in addition to just the generation of the trace itself by the model, there has to be additional functionality that provides for the data analytics that are needed in order to fully understand the results of the model itself. It's not just, okay, well, there's one error. There are 20 compliance reports embedded in the trace itself. There are innumerable numbers of waypoints that are worthwhile considering. And so exploratory data analysis, which is common in inspection of the output of models, has to be accommodated as well. And one of the true features of IPLCheck AI is that it provides that through a TOS command line, a TSO command line prompt that we'll talk about next. So with that said, let's look at what that might look like. Remember, I said that the trace itself, which is recorded in single sequential data set that we refer to as a log can be between 15 to 20,000 records long. Now, if you have SDSF, you could use the CK function to simply display all of the checks that have been run by the IBM Health Checker for ZOS and go find the ones that are associated with New Era. They're all prefixed with NEZ. The two that are critically important with IPLCheck are its ability to provide an understanding of dynamic changes that have been made to the environment. That's one of the checks. The other check is an operating system check. That is the full 9 yards of the ZOS operating system of the system that is executing at the time that the health checker runs. There are other checks which are possible. We call those advanced functions that essentially focus on IPSec and other security-related items. But for basic IPLCheck, it's dynamic changes and the operating system itself. Now, in addition to looking at the results under SDSF, you could also go to 3.4 and simply scroll the data set itself. And remember, that would be a daunting task because there's so much information included in it. Or you could choose to use our web-based interface, which you see hidden behind or partially hidden behind the upper panel, to do a deep dive into the content of the trace itself. Or you could use the line command that you see the dashboard resulting of it on the screen right now. So let me do that. Let me go to a TSO session that I have started and just simply type in TSO dollar command line interface dollar, or excuse me, *CK. So that's the command string that's necessary in order to display the panel that you see on the left-hand side. Now, you can enter that just about anywhere in an ISPF environment. You could enter it at 3.4. You could enter it at SDSF. You could enter it if you're in the log or any place that you might normally be doing your work. You don't have to go to some other special interface in order to gain access to this. You can just simply type this command string. So I'll go ahead and press return. Now what it's doing now is it's going out and it's reading the last log that was created by the IBM Health Checker for ZOS and disaggregating it into its relevant components in order to be able to display it in the form of a dashboard. So if I didn't lose my session, it should be good. Okay, I think I must have lost my session. Let me just shut this down real quick. Yeah, I had. Okay. All right, so same sequence, TSO dollar command line interface, CLI, *CK. Okay. When you give a live demo, sometimes things don't go exactly like you plan and you sweat a bit. So forgive me if I look like I'm sweating. All right, so here's our interface. And so what we've done is we've gone out and we've discovered the last inspection that log that contains the trace information that became available during that inspection. And this is it right here. And so if we wanted to see that, we could just put the cursor under it and press enter, and we would be in the equivalent of 3.4. So we could scroll down and look at it and have a great time in it. But if we go all the way down to the bottom, we can see in this case, this particular trace is 18,000 records long. And so doing a sort of visual review of the raw log itself and the trace information that's in it, as again, as I said, would be quite a daunting task. So let's take a look at some of the things that we can do that might make that easier. For example, all the findings have been broken out. So the errors, there are no errors. There are a lot of warnings. I'm on a development system, so security is light here. And so most of these 144 warnings are security related. There are some notices, and then there are some informational messages. So if I put the cursor under the 8 and press enter, then what I'm going to get is a listing of all those notice messages. And they'll be by message type. So all of the messages that are the same, for example, the 7694, are all grouped together so that you can get an understanding of the commonality of the problem that is being reported. And that common problem extends across all of these various data sets. And so um, something wasn't found on the volume it was supposed to be on. And in this case, they're all five of these are the same thing. We have an integrity problem reported here because link auth is equal to link list. That's an issue that needs to be addressed from an audit perspective and security perspective. And then we have some information about LPA and linked list having secondary allocations, which is not something I think you essentially want to do. So you don't have to go fishing around trying to find these. You can get an idea of how disparate these would be if you were searching the log itself. This one's on line 828, this one's on 567. 575, et cetera, et cetera. This one's on 1943. So you would spend quite a bit of time trying to come to a conclusion about what is the state of the, notice messages and what caused them across the entire log itself. Now, there is other information in here. For example, we're keeping track of the history that's associated with the inspections themselves. And so over time, you can see the age of the IPL. It's kind of an important piece of data. You can see how many errors, warnings, and notices. So you can see this has jumped up after the 5th of October. We fixed one problem, but we had additional warnings that occurred after that. So I'm looking right here, 122 versus 144. And you can see other related bits of information. For example, dynamic changes in symbols, APF list, BPX list, mount, LPA, link, RNL, and then changes. And I'll show you how you can get to those and create those really easily in just a second. So all this information is being tracked historically so you can see over time when a problem occurs, is it being resolved or does it linger? And so in some cases, problems were resolved, but then they came back and then they began to linger. So no actions have been taken to correct those specific problems at this particular point in time. If you're on a small system, if you're the only systems programmer, you might not be necessarily alarmed by this. But if you are someone who is coming in to assist in the evaluation of a system and its integrity, then this kind of reporting becomes critical so that you can see the care with which is being taken in order to resolve issues as they are reported by the model itself. Now, simply going back, we can look at more detail about how this system was actually started by putting the cursor under the load palm. And here we can see all the relevant detail associated with that. All of these things that are in white are all hot, just like you would on a website, so you can get to them immediately. Now, one of the advantages of IPLCheck AI is it allows you to build a baseline at any point in time. So I built a baseline, um, and right now, its age is 36 days old, okay? So if we are measuring against that particular baseline, we would find that there is one problem or one change. And so we could put the cursor under that, and it would tell us what that change is. Oops, sorry. So you can see here the changes in IEA-SIM. We deleted one line, this one. These are all play data sets, by the way. And we added 3 more. And so we can show you, oops, in the member itself, as it currently exists, where those 3 new lines are. So you can see one here, you can see one here, and you can see one here. So without that, it might not be clear to you that there had been an update to IEA-SIM, and that there had been a delete, and there had been some additions, and where they were. And IPLCheck AI and this interface allows you to actually see that. There are a number of other prompts here. We could, for example, say, let's take a look at all the prevailing keywords and their values. Here they all are. And in those cases where we actually have a director that is using a default value, and there is a published default, even though you haven't specified one, we will tell you what that default is, so you don't have to go guessing around for it. Rex associated one, default 00, catalog 00, CEA 00. So not only do we tell you what the keyword is, what the default is, or what the actual suffix is going to be, multiples of them, by the way. Let me get down here a bit. You can see in the case of the PROG member, all of these, no guessing, we know exactly where they're at. We know exactly where they were sourced from, i.e. WS. Or anything that you need to know, you can probably find it out here. Of course, there's a lot of information here still. That's going to take some time to become familiar with this and to understand exactly how to use this appropriately. We'd be more than happy to help you to accomplish that task. There are a number of functions here. You can print these, you can copy them, and you can email them as well to other people in your group. You can do searches against the log itself or against a trace. Here we have 4 predetermined queries, if you would, or searches. Messages, for example. This will tell us all appropriate message numbers and what records actually fell within those message groups. And because of the power of this, there's also a set of guardrails that can be set up to limit access to administrators, users, and auditors. And each one of these classes of users has their own specific interface. But right now, I'm an administrator, so I get access to this. But if I was an auditor, my access would be limited to this. I could see all the reports that are being requested. I could see the timing of when those reports are being made. I could see the delivery mechanisms that are being used to deliver the reports, email, ServiceNow, or FTP. FTP being supported for both regular FTP and secure FTP. So you can set that up, and when a report is ready, it'll be delivered via one of those two mechanisms for FTP. So a lot here and a lot more to get into should you choose to have a more in-depth client briefing. All right, so let me go back to the left-hand side here and talk about another kind of problem that you may be faced with, maybe not today, but at some time in the future. With 3.2, actually roll back to 3.1, IBM introduced the concept of the clean room. That is an environment where resources, sysres volumes, LPA list, linked list, other critical components could be signed using a combination of key rings and digital certificates in order to accomplish that task. Now, there's some advantages to doing that. There are some integrity gains to be had by doing it, and there's also some work that has to go into it to make it possible. The advantage is that individuals can be assigned the responsibility to sign those resources. And once they are signed and the appropriate certificates passed on to those users who will actually perform a secure boot so they can load it in the HMC, those signed resources will be evaluated to make sure that they haven't changed in any way whatsoever. And if they have changed, one or two outcomes can occur. There could either be the reporting of a warning, and or there could be an absolute entry of a wait state until the problem is actually resolved. Now, is all of that really necessary? Well, again, if you're a small shop and you're in control of everything that goes on and you have a trusted group, probably not. But to improve the overall integrity of your group, or if you are working in a larger group where there are multiple people who have responsibility for upgrading and maintaining various different systems, it may be a good idea to begin to give individuals signing responsibility for the systems that they specifically are responsible for. Now, in order to do that, you're going to have to master a number of different constructs and how to create key rings, how to create the related certificates, how to create the related profiles, both our data log profiles and facility class profiles, and the certificates that are associated with the signings that need to be attached to the key ring itself. So what you see on the screen now is an interface that would allow you to do that relatively easy. Now, I'm going to go back to the right-hand side now, and on the command line, I'm going to type TSO, dollar, command line interface, comma, VB for VALBoot. It's the name of the tool, VALBoot AI. and press enter. So here's a relatively straightforward interface for creating the key rings and the certificates themselves. Now, this AI is quite different from the one that we looked at. This one, you play a major role in providing information, prompts, to the model in order for it to do its job. The model itself was trained by the data scientists here at New Era in how to build key rings of various different kinds, how to build certificates of various different kinds, how to permit them, how to profile them in a scripted way that ensures that they can be used for signing those resources that are critical to the overall integrity of the ZOS environment. So let's go ahead and let me give you an example, and I'll build one for you. For example, I could type in a user, excuse me, I typed in Aroby1 and say, okay, I want to build a key ring for him. Now, there are 4 specific ways in which key rings can be built. There are very generalized ways in which everyone could participate in the key ring itself, which is not considered a best practice because the signings could not be traced back to an individual. It's convenient, it's flexible, but it doesn't give you the control that you need, and this is relatively simple to do. So what I'm going to do is just create it for one individual. Validated boot signing keyring is a default name for the keyring itself. It will be appended with the label Aroby1 when I come down here and select Create Update Profile Keyring. So here's what the model has come back with. It's saying, from the information you gave me, here are the RACD cert, the our data lab and facility class, commands, permits, and profiles that will need to be created in order to accomplish the task of building a keyring that will ultimately support certificates that will be linked to it. And so you can see up at the top here that the keyring now is going to be created by RACD cert. I'm going to be the owner, PRoby1, and Aroby1 will actually have access to this keyring as part of the signing process. Now, when we go down and take a look at the further detail, here's the R Data Lab class profile, we can see that the profile has me as the owner, obviously that would be correct, and Aroby1 as part of the keyring name with .list on the back end of it, which is a requirement for all our data lab profiles that deal with keyrings. We're going to permit some additional individuals to this. Aroby1 will be permitted. We need to do that because I'm the owner. We could permit other people to the keyring if we wanted to. We're going to build a facility class profile. RR program V2 signing PRoby1. This is a default required by the system, not by our system, but by the signing systems themselves. This is the owner of the profile. In addition to the profile itself, this particular, or in addition to the naming of the profile, this profile also has to include an APPL data segment that defines the keyring that will be used in the signing. Now, why is this important? Because through the signing process, the first thing that's going to happen is that the system is going to attempt to find this profile. And if it does, it's going to extract this keyring, and it's going to figure out whether or not ARoBie1 has access to that keyring. And if it does, then ARoBie1 will be able to sign using that keyring. But the linkage here is between this facility class profile and this APPL data component that links this back to the keyring itself. So now if we want to build a keyring, just press add to profile and permit. And all of that has been done. Here's a trace of that. Could examine that. When I PF3 out, it comes back and it tells me, okay, so here's the keyring that you built, and it seems to be okay. And we could list the details of it. No certificates have been assigned to it yet. We could look at its profile. 2 people have access to it. This again to validate the construction and to give you a chance to explore it in the easiest possible way so that you can validate that it appears to be correct. Now, when I go back, now I have to build some certificates to put on it. And so the easiest way to build those certificates is to provide a suffix. So I'm going to provide the suffix A1. I'm going to provide a common name. I'm going to provide a company name. Now the suffixes have to be the same. So you might be asking yourself a question now. Why do we have 2 certificates? The reason for that is that in this process, we are going to act as a certificate authority for the signing certificate. So the first certificate up here at the top is that certificate authority certificate. And it is this certificate that will be used to sign this certificate, which is the actual signing certificate that will be used in the signing of the resources themselves. So right now we have a keyring. Right now we've defined the excuse me, the CA certificate with a suffix of PROB1, and the signing certificate, ARoBie1, and the signing certificate with the suffix ARoBie1. Now, these are necessary because when we, at some point, are faced with an expiring certificate and we want to renew it, we will need to renew both the Cert-Auth certificate, that is the CA certificate, and the signing certificate at the same time. Okay? All right, so we are set up the way that we need to do it, and we'll go forward. So here's what the model came back and said. Based on that prompt, based on the information you gave me, I'm about to generate some certificates using these commands. I'm going to link them to this keyring, the one we built earlier, and I'm going to generate them with a label, CA ARoBie1. I'm going to sign it with that certificate. and I'm going to build the signing certificate with this label, SG. I have all of this additional subject information, SysProg, VALBoot signing, new era, US, all of that got filled in automatically for me. I have an alternate name. I have information about how the key will be used. All that it comes from documentation and white papers that have been written on this topic. I have a date that got filled in automatically. This is going to be good for 1 year. And importantly, this guy is also going to store the private key using a NIST algorithm and the PKDS under the name SG Arobi 1, and the size of that key will be 512. In the case of the one above, the Cert Auth certificate or the CA certificate, we're going to use an RSA key, put it in the PKDS. We're going to assign it the CA name, and the size of it is going to be a key of 4,096 bytes. So this is about as secure as it gets. So remember, what we're doing here is creating the certificates. First, the CA certificate, storing its private key in the PKDS, then creating the signing certificate, actually signing it with the CA certificate, and storing its key in the PKDS with a NIST ECC type key of a size 512. So here we go. This takes a bit of time because of the size of this RSA key. Most scholars will tell you that these elliptical curve keys are more efficient and highly secure. Anyway, everything completed, no replies. We can follow the trace of what actually happened here. When we PF3 out, we now see that our keyring has two certificates attached to it. So if we list the keyring, we can see the certificates that are in it, and we can list the certificates themselves. Now, this listing of the certificates is not just the certificate itself. It's the profiles and permits that are associated with that certificate. So you can see them here, PRoby1 alter, ARoby1 read, our data log profile, what it is and who's got rights to it, what connected certificates are associated with the particular keyring, which was up here. I forgot to point that out. Here's the keyring itself. And then information about the PKDS label. Okay. We haven't done very much to it, so not much of a change, but you can see that it's there and who's permitted to it. So all the actions that were necessary to set this up have been accomplished. Let me do one other thing because I know we're getting close to time here. Once key rings and everything are in place and certificates have been signed, the question often becomes, is this thing still signed? Well, let's have a look. Here's a place for you to audit a specific data set to see if it is signed or not. And this one does happen to be signed. And you can see in the audit that we just ran, that signing still remains good. It remains successful. Now, when I PF3 out, I see that the libraries themselves are not signed. So what I'm going to do is go and sign it. By the way, these are all the valid key rings. These are all the people who have access to them. I'm going to sign it with my ID. I can do that. I'm going to sign it in place. By the way, before I do that, let me just show you something here real quick. This is what the content of this module looks like before we sign it. Okay, so I don't know, how many lines is that? 8 or so? I PF3 out and I come back and I say, yes, I would like to sign that. Now I can sign it in place, or I can sign it and have the signed version of it show up as a private library. Excuse me just a minute. So this is the JCL that will be needed for signing. We can see that the in file is the system we are trying to sign. The out file is the same because we're signing in place. PF3. We can post to the control journal if we want to. Process says everything was successful. Show the findings. So here are all the details again of that particular data set. Now here's an important thing. Once you get one of these data sets signed, you're actually going to have to export it so that it can be imported into the HMC. So sending it over to those guys can turn out to be a bit of a problem. So here's a nice, simple way of accomplishing that. So all of the necessary values have been filled in, and all you need to do is just select this and export it, and it will be exported into this particular data set. Okay, let me PF3 back. So I'm pretty sure you appreciate by now that there are lots of steps here. Here's the audit I was trying to do earlier, but I hadn't signed it yet. So here's its fingerprint. Here's its subject key ID. Just one final detail point here. Fingerprints are used to sign certificates. Subject key IDs are used to sign volumes. We're doing an audit of a volume. And you can see down here at the bottom that the subject key ID was used and not the fingerprint itself. Okay. Hey, listen, if you want to get more into this, we'll be happy to do it. Again, client briefing is always available. Okay, so back on the left-hand side, the question always is, what is the general case for AI-driven assistance? I mean, why beyond just it's a complex problem and I need somebody to help me? Why? Well, part of the reason is that as groups get larger, or new people come into the group to take over responsibility of system programming, perhaps next gens, coordination with them becomes absolutely critical to advancing their understanding and providing them with a platform that can assist them in onboarding. AI models of the kind that we've looked at here, IPLCheck AI and VALBoot AI, can help to communicate concepts that are necessary in order for them to be able to do their job. What do I have to specify in order to create a keyring? What do I have to specify in order to create a certificate? What do I have to do in order to change the way in which the system is configured, and how can I test that before I actually make that change? A job for Image Focus and his new release analysis capability, what if capability. Also consistency. Once the AI is set up and it's groomed to your requirements, remember, you are the decision scientist here determining whether or not this all makes sense. But once it does, then the application of it can be consistently applied over and over and over again. No guessing. Everything is saved. Everything can be repeated. And because there are baselining capabilities built into IPLCheck AI, comparisons begin to become possible to understand how things are changing. And because we maintain histories, you can not only see the change from one execution to the next, but you can see the changes over time to determine the care that's being taken of the systems themselves. I hope you've enjoyed this. I really enjoyed presenting it to you. I want to thank you for coming out and sharing your day with us. We'll be back with a thankful story about the control editor. We call it TCEAI on November 20th at 8 a.m. Pacific. So look for an invite for that. I think you'll find it equally interesting. Thanks again.